presentation is for evolution of the statistical downscaling research at the University of Western Ontario from KN and weather generator to physically scaling method.
Thank you very much. Hugh Gill, thank you very much for inviting me and giving me an opportunity to kind of share with you a little bit of our work. I decided in this presentation to kind of go over the longer period of time that our lab and the work on impacts of climate change, with focus only on reviewing the downscaling tools developed, and hopefully give you an impression what we are up to and where we are with our research. To begin, I would like to introduce our lab. Some of the people sitting here were part of that research environment, and it is a computer-based research laboratory with most of my students, postdocs, are kind of working together. Our focus is on the application of systems modeling, the risk and reliability, and the implementation in water resources management. In 2014, we celebrated 25 years, and many people went through the lab. As you can see, the numbers, and considerable research funding was managed. Outcomes of the work are, papers, books, some of them translated, and also this is, I think, an interesting product. The lab is printing kind of gray literature type of reports where we provide the details of different research projects. And from 2011, the university library took over the distribution of this so-called the blue books or water resources research reports, and they're regularly sending me information, and I'm really surprised, the impact. You see from 2011 about 50,000 downloads of these documents, where my citation index is, like 5,000-6,000. So it seems that the work and the research and the results presented in this form are attracting other researchers, and that's another way how I think this research gets around. These are the current research projects, and number of them, as you can see, are related to impacts of climate change. We are finishing very large-scale project with the 4 different coastal megacities: the Vancouver in Canada, Manila in Philippines, Bangkok in Thailand, and Lagos in Nigeria, where all cities are selected on the basis that they're exposed to the same hazards, sea level rise combined with the flooding because of the large rivers flowing through the cities. And we are trying to see how the cities can kind of adapt and what will be the best way of adaptation to these changing conditions. Looking into extreme flows under changing climatic conditions in another project. Building capacity in the context of global change here. Beside the climate, we are considering integrated impacts on the increase of population, change in land use, and change in climatic conditions. And then some work related to kind of modeling risk, and I am switching from risk now to resilience and developing the quantitative measures of resilience that can help us assess, as you can see in the hydropower infrastructure systems, and weigh how these systems manage to dealing with the insurance. This is actually a project with a very large reinsurance company where we are looking at different hazards from earthquake, flooding, and wind impacts, and how kind of common risk across these hazards can be assessed. So this is giving you the kind of introduction what the FITS is. FITS is the short for the Facility for Intelligent Decision Support in Water Resources and Environmental Management. The name given to the lab a long time ago when I established it at the University of Manitoba. And there are 2 kind of philosophical principles that we're applying to many studies, and I think it's linked also, these are linked to also what I will be talking about, the climate change and downscaling. The first one, the first principle is that the system's kind of view of the problems that we are dealing with is A little bit different. My background is engineering. I have a very strong bias in systems and use of systems analysis. But the problems we're dealing with are the problems from the social sciences domain. We are actually talking about, systems of people, organizations, societies, all embedded in the environment and connected with two types of flows of resources and information. And that kind of gives a very different context to our kind of research and approaches and the methods being used, where we need to find out how the information determines the resources being used by different subsystems, and where the values are playing very important role because of the social orientation, because they are used to provide the meaning to information. And the second philosophical principle underlining all the studies is, risk management or proactive risk management, where the traditional kind of steps in identifying risk, communicating risk, and so on are being embedded in the process of managing risk and using the risk management as one of the adaptation strategies to changing conditions, in particular, to changing climatic conditions. And that's enough about the lab and about our research. I'll be giving in this presentation the kind of overview of the research that probably goes in our lab for last 12, 13 years, and many research projects that were giving us opportunity to kind of continue with the focus on climate change impact analysis and development of different tools for supporting the process. These are the conclusions of my presentation today, that the global climate is definitely changing very rapidly, but understanding impacts at the local scale is still of very high importance, and I think this is why we are here, these 2 days, to see how can we bring these global issues to a local scale, and see how we can improve our understanding and develop different adaptation strategies at the local level. Statistical downscaling in the process is a reliable way to downscale the global data to local scales, and I'll be talking a little bit more about that. I'll be talking about 2 products that belong to this class of statistical downscaling tools. One is the KNN-based weather generator, and another one is maximum entropy-based weather generator. They both found out to be reliable and important tools for future climate predictions. And I'll end up the presentation with a method that is, for the first time, I think, using statistical downscaling and bringing into statistical downscaling some physical information. We call this method physical scaling, in order to kind of bridge the gap between the statistical and dynamic downscaling methods. The picture I have here is, I don't know how many of you are aware, but Canada went through still kind of dealing with a very large fire in the central part of Canada, in the province of Alberta. And it's a kind of ironic outcome of this picture. This is the area that has been developed because of the oil exploration and use of the oil sands for feeding the society that depends on the fossil fuel, and the process and the fire affected the city community of about Fort McMurray, about 150,000 people, about 90,000 of people being evacuated using one road, and many of these vehicles that are using these fossil fuels were abandoned because of the lack of gas during that process. So you see that kind of interaction between the society that depends so much on the fossil fuels and fire that is being the consequence of the changing conditions. Alberta experienced extremely dry period without the rain and above normal temperatures during the period when the fire started. I'll talk about the motivation. I mean, this is a very knowledgeable group, and a couple of things that I prepared as introduction are probably not going to make too much sense. but I'll repeat them anyhow. And then talk about these three different downscaling tools and or approaches that we developed in our lab, and visit again the conclusions that I started with. Many people were involved in this research, members of my team, from some master students, Ms. Sarah Irvine, Ms. Liana King, Dr. Kyung-il was with us as a postdoc for a period of time, and he was contributing to that KNN weather generator that I'll be talking about a little bit. Another postdoctoral fellow, Dr. Srivastav, contributed to the development of the maximum entropy-based weather generator, and Dr. Gaur, who is now continuing as a postdoctoral fellow, is the author of this physical scaling tool that we are right now using, improving, and trying to publish in order to inform the community. There were a number of projects that supported the climate change research in our lab, and they were very kind of interesting. Most of my work is, grounded in the practical issues, being in engineering and dealing with the problems that engineering community has. We had a set of studies dealing with the impacts, finding out how to assess the impacts of climate change on the watershed of the river where the city of London is located. It's the Thames River. And in this set of I think we had three different projects. We developed initial ideas how to move from the global scale to a local scale, what to do in order to downscale the information, investigated different tools, and that initiated the development of the tool that finally we call ours. Then we had another project, I think Dr. Kyung-il was involved with that project. That was basically a project for the city of London, where the city was very much interested on the impacts of climate change on the municipal infrastructure. So they gave us a very strict kind of set of conditions and requirements to see how the local municipal infrastructure is going to be affected by the potential impacts of climate change. And based on the previous studies in the basin, we identified that the consequences of the climate change in this particular location will be mostly visible through the increase in frequency and magnitude of flooding, and that study actually went into that direction to assess the impacts on infrastructure. And the third, this particular study was followed with two smaller studies, and some work done for the insurance industry, and also for the development of the tool to support the Canadian community in updating IDF curves, intensity, duration, frequency curves under the changing climate. This tool is now public, and it's being used, and did incorporate a number of things, especially the downscaling tools and the procedures developed in other projects. We have approximately 470 users registered right now. Very broadly, 2 of the provinces in Canada are mandating use of this tool for all the work being done. And it's pretty interesting to see how the need for the practical solutions and the ways how to bring the climate change research into engineering practice actually led to this interest and use of the research results. This is my kind of intro, and you're all aware that we are seeing the change of the in climatic conditions. This is the reality. It's a part of the definitely broader picture, because we are not seeing only the climate change. We see increase in population. We see massive change in the land use, especially very heavy urbanization and movement from the rural into urban communities. And also we see this kind of impact of anthropogenic activities on climate. I mean, these are the IPCC results where now it's kind of agreed completely that humans definitely affect the climate, and that is being mostly done through the emissions and increase of the concentration of the greenhouse gases. This is another important consequence, that if you look at the global change and if you look at the change on the local level, that there are differences. And this is the picture from the central England, where the global temperature change is represented with the red line, and the kind of local temperature with the black line, so that you can see the difference. You can see the kind of agreement between on annual, decadal, and multi-decadal level, and that's I think clearly sending the message that we need to find the way how can we understand or improve our understanding of the changing conditions on the local level, and be careful how do we use the information from the global level. Two types of approaches are being used. I think a number of you already mentioned them. I am summarizing here only the kind of some pros and cons for the statistical and dynamic downscaling. I think these facts are quite known. Computational requirements on a dynamic, scaling very extensive. On a statistical, much simpler, efficient, and definitely cheaper. Fast real-time operations possible with use of the statistical tools. Time-consuming and real-time operations still questionable with the use of the dynamic downscaling tools. The statistical downscaling has some problems in the data sparse regions, the reason being that they are basically establishing the relationships between the observed and global climate information. And dynamic, I think, is much more efficient in these particular regions. The statistical also tools are more relevant in the similar climate conditions, where the dynamic tools are equally relevant in drastically changed future climates. But we have also to kind of remind ourselves that even this regional type of more detailed kind of physical models are being developed by utilizing the boundary conditions that are coming from the global climate models. So the link between the global information and information derived on a local scale is still present even in this very demanding and much more detailed physically based type of tools. Our work was, the work in our lab was mostly within this area of the statistical downscaling tools. This is how we started, because many of these practical projects did have requirements of kind of efficiency, as well as the kind of potential use in the practical real-time conditions. Statistical downscaling kind of methods can be used in many different ways. I think you all worked on that, used them. The presentations, up to now, we're already illustrating very wide range of potential applications. I'm generalizing here, filling missing hydrological information to assessing the impact of climate change is definitely, or are definitely the kind of key applications. And there are a number of potential examples and tools available, from parametric, semi-parametric to non-parametric tools. And our work is mostly in this particular area of non-parametric tools, focusing on these two approaches. I'll provide a little bit more details on these two. Generally, the weather generator or the implementation of weather generators involves two different steps: incorporation of the climate change signal as the first step, and then generation of the synthetic replicates. So in this kind of process, we develop the kind of change factors. They depend on the kind of quantile considered, and we have to be quite aware. This scattered plot here of the various climate models and scenarios linking the absolute change in temperature and percent change in the precipitation are telling you, if you go for the kind of links that are on average conditions, we may miss some combinations. We may miss some combinations of conditions that may be more extreme. So the choice in selecting a model, selecting a scenario, has to take that into consideration. In the generation of the replicates, preservation of the spatio-temporal structure, and finding ways how to generate the extremes outside of the observed range, performing the multiple runs to account for internal variability are all the pretty serious questions that kind of every research work or development in this area is are dealing with these questions. So the first tool developed in the lab was based on the K nearest neighbor algorithm that was introduced some time ago in the literature, and we started from really basic form of that generator, reaching the version 4, which is the most recent version that is now being available and running pretty smoothly. The process of K nearest neighbor algorithm starts with the selection of the nearest neighbors, where you choose the temporal window, select the subset of potential neighbor days within that window, calculating the distance of each potential neighbor day from that reference day, and then selecting the closest K nearest neighbor days based on that distance. The final step in this process is selection of one of the K nearest neighbors to become now the step, or to become the reference day for the next step, and this is how we proceed with the algorithm. In the process, we are also dealing with the consideration of multiple sites and variables, and nearest neighbor, whether is considered at all sites in order to preserve the spatial correlation. Dr. Young actually added the principal component analysis to improve the computational efficiency of the algorithm, and we did that to reduce the kind of these requirements while considering multiple variables, and I think our findings were that the only first principal component considered was sufficient in explaining and contributing, and that's where or what we continue using in the process. The final step, or the third step, is inclusion of the random interval variability component. So the development of this perturbation component to facilitate the values outside or estimate the values outside of the observed domain was very important. The original idea of the KNN include the perturbation. This was added later through the parameter, one parameter. And what we have done here, we also improved the resampling procedure by performing the resampling using the time blocks of the particular length to deal with the temporal structure. So the kind of general conclusions based on our applications were that the time blocks of 10 days and the parameter length of 0.9 with basically 10% perturbation, we're typically giving pretty good results. So this is the kind of fast set of steps how the KNN generator works. These are some of the results of the work in this particular one. This is in the Thames River watershed. We used 22 stations, 27 years of historical information. We generated 25 ensembles of synthetic historical outcomes, and what you see are the two graphs summarizing the total monthly precipitation and daily precipitation characteristic, basically the mean, simulated mean and standard deviation. The numbers here are basically 25 points or 25 generated. As you can see, the performance was pretty good. The line represents the kind of historical. The medians are following the observations. If you look at the daily precipitation, you see that the spread around the mean and spread around the standard deviation are very much concentrated, and therefore kind of giving us for conclusion that the performance is acceptable. We evaluated the performance using the traditional set of indices for the evaluation. A couple of publications out of this work are available, and you can see the details of the evaluation. The second, forgot to mention that the implementation of the procedure is done in the form of the decision support system. What you see is a relatively simple interface that provides the link to the vendor-generated version 4. This type of interface is created for the users without, detailed knowledge on the downscaling and understanding of the downscaling tools for the practical application. They just follow the interface in order to prepare the data, identify what are the parameters, and basically simulate or generate outcomes as many times as they want. I forgot to mention that this particular tool is quite demanding, computationally quite demanding. On the PCs with i7 processor and I don't know how many bytes of memory, takes about 25 minutes to kind of run this particular one. And that motivated us to look at some other options. And the key research outcome that came from investigating other option is this multivariate weather generator based on a maximum entropy bootstrap. In this particular work, this is available in the climate dynamics. In this particular work, we focused on two different major steps. First one, incorporating in the process of downscaling this maximum entropy bootstrap that does not depend on the resampling, random or conditional of historical data, but is basically very well suited to random generation on time series with a strong temporal dependent structure. The random generation is performed using empirical distribution function with endpoints, and endpoints are determined to basically allow limited extrapolation. We use the trimmed mean and 10% to do that. Reordering of the random series is being done to respect the rank ordering of the original time series and basically preserve the temporal dependent structure. The other step within this particular tool or the other process is the process of orthogonal transformation, which is introduced for the to preserve or capture the multicollinear structure between the weather variables at multiple sites. This transformation is synonymous to principal component analysis, and the kind of main objective of introducing this particular transformation was to capture the functional relationship between the weather variables within and among the various sites, basically the spatial correlation. So the implementation goes through three different steps. We have a detailed algorithm. The climate dynamics paper is discussing the theory and showing lots of results and verifications. And we have also paper in the environmental software journal, which is presenting the process. And the process involves these three steps: application of orthogonal transformation to spatially correlated weather variables at different sites, and then use of the maximum entropy bootstrap to generate synthetic replicates, and then finally return or implement inverse orthogonal transformation to restore the spatial correlation of the weather variables at different sites. So this particular tool was assessed in a number of different ways. These are some of the results which are showing the kind of precipitation maximum and minimum temperature and the preservation of the mean and standard deviation. The historical are in black and synthetic in red. And as you can see, the results are pretty good here. The important was the comparison that we did between this particular tool and the previous one, the KNN weather generator, and the comparison is showing actually that this particular approach is much more efficient, computationally much more efficient. It takes about 30 seconds compared to 25 minutes of the KNN weather generator. It's not restricted in any way, and it's relatively simple to use because in the KNN weather generator you need to experiment with a number of parameters that are affecting the downscaling process, whereas this particular tool is relatively simple. Going through these steps is straightforward without choice of any particular parameter. We did notice some differences, especially in the precipitation between the two tools. The maximum entropy model shows very good dispersion of the data in comparison to KNN algorithm, but KNN provided considerable smoothing in the lower values of the precipitation, but not near the extremes. So they both have their own kind of good and weaker points, and obviously if anyone is interested, it would definitely require some testing and implementation in the local conditions in order to assess the utility or potential use of a tool like this. The third tool developed in the lab is very recent actually. The research was mostly conducted by Dr. Gower, who was developing this physical scaling method, which is completely not location specific. And the idea in this physical scaling was not explored up to now. The statistical downscaling was obviously not, and one of the main criticism involves the idea that we assume that the relationship between the observed and the climate variables historical remains the same in the future, so we are not able to address the potential non-stationarity. And in this work, I think for the first time, we succeeded bringing and at least partially touching the question of non-stationarity, and this has been done by bringing the local physical properties, land cover and elevation and their configuration as predictors, combining with the climate kind of variables through these relationships, and using the future predictions of these changing physical conditions actually use or generate the information. Downscale information that is partially, I think, responding or addressing non-stationarity. The kind of justification for this kind of local scale change is nicely shown here, the difference between the night and day kind of temperature, which is obviously pointing out and the kind of local impacts, and I think there are probably a number of similar illustrations that can be used to justify that. And in this particular approach, I think for the first time we try to see how this information on different locations can be, physical information can be enhancing the statistical downscaling process. So the two different versions of the physical scaling method are proposed. The one is just called the physical scaling, and another one is called the physical scaling with the surrounding pixel information. My student, Dr. Gower, is claiming that he on purpose selected the names. This particular tool, the acronym is SP, and this one is SPS, and the SPS are the initials of my name, and he decided to kind of name the tool after his advisor. I was really flattered to kind of learn that. I was reviewing the work, I didn't realize that it has anything to do with my name. Anyhow, in the physical, in the first kind of tool, we were focusing on the large-scale climate impacts and combination with elevation and land cover. In the physical scaling with the surrounding pixel information, we actually brought the neighborhood information on land cover and elevation and combined with the with the information from the previous one. Temperature is kind of modeled using the kind of regression equation that kind of combines the climate with the elevation and cover in a relatively simple way. And the precipitation is modeled in the two-stage process where the occurrence of precipitation is modeled with this type of a regression relationship, and the amount of wet days as a second step is modeled using the generalized additive model. This is the logistic, this is the kind of logistic regression-based type of model, and what we kind of achieved in this too is to kind of bring the large-scale climate through this particular variable temperature and the precipitation from the climate or the global scale, and then bring the elevation into the equations on kind of both different models. These two physical factors are the kind of key additions that are modifying, I think, the procedure compared to any other work done in the statistical downscaling. For the second group, we have a number of elements that are bringing basically the neighborhood information, again, the physical information, land cover and elevation of the neighboring pixels. So there are kind of these kind of scales being considered with the different number of pixels, the close neighborhood up to 9 by 9 as a larger neighborhood. So the idea was that the land cover and the elevation may have some of this kind of more regional characteristics, and picking them up, and especially when you look at we were looking in this particular case 14 different land use classes and so on. That additional information can be pretty useful. So this is done on a pixel by pixel basis, so you see that you're getting very detailed description of the physical conditions. So we ended up with a number of models that are then further assessed, evaluated, compared with the other downscaling tools. The first one that used the climate variable, the land use and elevation. The second one was ignoring basically land use and evaluation, and we used that as a reference in order to see is the incorporation of these two physical characteristics really bringing some important change into the downscaling process. And then the remaining models were the models that were using different size of the neighborhood around. So you see 3 by 3 to 9 by 9, combining all the climate, land cover, elevation, and the land cover and elevation of the neighboring cells. So this is the kind of number of models that are being used. We implemented and tested the procedure using the region in Saskatchewan. This is a central Canada, Canadian prairies, very flat region. The dots here are showing the number of stations, Environment Canada managed stations, and these 4 watersheds were selected, small scale watersheds were selected in order to assess the impact of different type of watersheds in different locations on the performance of the weather generator. This particular region is very specific, covered with many small lakes and streams with altitude between 250 and 1400 meters above sea level. with the continental climate, with the large fluctuations up to 65 degrees, cold winters, hot summers, and with the different land covers. As I pointed out, we identified 14 different groups and 4 catchments for the assessment. Cropland and forest are the 2 major, land covers in the region, but further detailed land cover data was extracted from the available data. The procedure is pretty demanding from the data point of view, and these are the type of data utilized in the development of this implementation of this downscaling process. We utilize the remotely sensed products like MODIS and SRTM for elevation and surface temperature and cover. We use the model-based products like NAR and CMIP5 for surface temperature, air temperature, precipitation. We use the observations, or Environment Canada observed data, temperature and precipitation, land use, observed flow data, and UNSPLIN as a gridded precipitation for maximum temperature and minimum temperature. So all this information for that particular region is downloaded and available now within our lab, and it's being utilized in other research projects, but was basically serving the process of development of this particular tool. So this is a very important piece of information. That's basically the available future land use projections that can be actually now used with the downscaling tool to kind of bring this physical information into the process. These are some of the results of the performance, assessment of the performance. In the first graph on the left-hand side, you can see how this is basically NAR analysis data downscaled to predict the MODIS surface temperature. This is a mean land cover trends, and they're kind of capturing pretty well the observed results. We have this type of analysis done for all the stations within the regions. There are some differences. This is obviously very well agreement, and I wanted to show the good results. There are some results where we are not getting the same type of agreement. On the right-hand side, we try to actually use the 7 different indices and compare various models. So all these are the downscaling tools that are based on this physical scaling method, and some of the available other downscaling tools, and see how they perform. So the conclusion here is the lighter area basically shows the higher performance. So if you look at along the spectrum of various modifications of physical scaling, they're all performing pretty well. There is no major contribution or improvement coming from increase or bringing more surrounding information or the neighborhood information. And another conclusion very clearly is that this physical scaling is obviously outperforming any other tool that we were comparing this particular one to. The next piece of information I extracted is also showing some interesting outcomes. What we are seeing here is the comparison of an assumption how much and how big is the contribution of these physical factors. So we compared the statistical, the hypothesis, acceptance of the hypothesis that the downscaling tool without the elevation and land cover compared to the tools with elevation and land cover are not coming from the same population. use the Wilcoxon sign rank test, and as you can see, the green is basically showing that contribution, precipitation, temperature, and flow for these 4 selected catchments and for 3 different climate models and all these different downscaling tools that we have developed. So the kind of the summary is that approximately 70% of the scenarios are showing significant, statistically significant impact or contribution of the physical factors, basically improving or producing different results from the weather generator without incorporation of that. We also try to measure the impact or magnitude of the change, and this particular graph is trying to illustrate again for precipitation, temperature, and flow. We utilize Sacramento model for these 4 catchments. These results are averaged over this 4 catchment and over the period from 2014 to 2100. And these are the different downscaling, the versions of the downscaling tool. This is absolute increase. This is a percent change in the precipitation and flow. And you can see that there are differences between the models. We concluded that uncertainty associated with different climate kind of models and different emission scenarios combinations are very significant. Changes are definitely catchment specific. You see how they are different in some catchments and depend on the location, depend on the size. We are seeing increase or decrease. And we found that the changes are a bit more sensitive to the downscaling model used in the case of the precipitation and flow, while the temperature changes were more sensitive to the choice of the GCM. I didn't bring we have actually the graphs where we assess the sensitivity. This is why I asked the question. We assess the sensitivity to choice of the climate model, choice of the emission scenario, choice of the downscaling, and for these 4 different catchments, and we produce these kind of results, and that's the finding. I mean, I'm sure that this is location specific, and in different locations you will have a different dependence. We also did the comparison of the land cover change or magnitude of land cover change in the flood magnitudes. So this is the change in the flood magnitude in percent for different return periods and different scenarios, different downscaling tools, again for these 4 different catchments, and again averaged over the return period. So the changes are higher for low flow return periods. That's kind of visible in the graphs. Larger uncertainty exists depending on the choice of the downscaling, GCM, and emission scenarios. Again, the difference exists between different catchments, so their changes are catchment specific, and the change is more sensitive to the choice of return period of the downscaling model. That's for this particular type of analysis. We didn't go deep into various hydrologic models and uncertainties that may be introduced in the process with the choice of different hydrologic model. We opted for the single model that was calibrated and available for this particular region. That was in Sacramento, and we utilized only one. So that brings me back to my conclusions that we see the impacts of changing climate, and we are observing very rapid change of the conditions, which are on the local scales bringing tons of different questions and issues. Some of them may be in this very dramatic form. Statistical downscaling, I think, is still very valid and reliable way of bringing down the global information to local scales. I think the 2 tools that we developed, pure statistical tools that we developed, the KNN and the maximum entropy bootstrap, are reliable and perform quite well. And the method like physical scaling, actually it's adding a new quality to downscaling process. by bringing this kind of physical information into the statistical process, giving us opportunity to now basically develop the downscaling tool that is potentially responding to the non-stationarity in this process. Through my website and this particular part, you can find lots of these papers available for download. I selected only the most representative. We have a number of papers dealing with the KNN. We have 2 papers dealing with the maximum entropy-based bootstrapping method, and we have 3 papers dealing with the scaling, but these papers are still in the process of, we have responses to 2 of them, and the 3rd one is still waiting for the response. So the moment when they become available, I put them on the website, and if you're interested, you can follow up and obtain this information. Thank you very much. I'll be happy to answer some questions.
I'm interested about your study, physical study method. How did you do the future projection? For example, if I want to know the 2050 or 20...
The future land use predictions?
Yeah.
I said this is available. We didn't do that. That information is available. This is being done, and we just utilize this particular project provided the very detailed future land use projections, and that's what we use.
Oh,
Yeah.
So
This particular project is focusing on a lot of different elements that are affecting the land use, the process of the change of the land use, and so on. I am not saying that this is how the future kind of look like, but it's considered to be the pretty significant source of information on the future land use. So this is a very important fact. I mean, without this, we will not be able to do that. Yeah.
So I have a couple of questions.
Yeah.
So in your physical scaling, you are introducing other sources of uncertainty in your scaling model. Yes.
Yeah.
Aside from the paleontological variable, you have
Now the physical. Yeah.
physical variables.
land
which
cover.
are
Land cover.
varying time and space and varying space. Well, assuming the topography or elevation will not change drastically unless we have a change in polarity between
Yeah.
south and north
Yeah.
magnetic
Yeah.
field. How do you think about the uncertainty issue?
We did go into that. This particular research did go into the assessment of the uncertainty, but we didn't go into assessing the uncertainty that being, for example, brought through the particular variable. That as we kind of look at that whole process of the impact assessment and what is kind of affecting the uncertainty. So I said we focused on the choice of global model, choice of emission scenario, and then the difference between these 5 different downscaling tools. So we were focusing on the including or not including land cover and elevation, including a land cover and elevation with surrounding areas and so on. So we looked at these 6 of them and then assessed the uncertainty that exists. So I cannot answer directly question, for example, how much uncertainty is being contributed by the change in or the uncertainty in these predictions, but I can say how the overall model uncertainty compares to another model.
yeah, I was thinking about if you can build a field bank. For example, if your temperature increase, rainfall increase, you will get more vegetation and unusual change. This is a spectrum model, so which is
there's no
But-
feedback in there.
no feedback.
There's no
But-
feedback in there because you're not using a physical model to ingest it again. Right. But then assuming that this kind of land use projection is
Is
in the final model itself, so the feedback is in there. then you're using again this as a covariate to scale.
Yeah.
So I don't know. So in the selection of these covariates, did you use like entropy, for example, or mutual information to see if why these are selected as viable? Why not clay? Why not sand?
No.
As my physical
No,
scalar.
it was based on basically the whole thinking along the line, what is contributing
course,
to
I'm
kind of
designing
climate, and what is affecting the locally the information and so on. So we didn't there is no kind of particular justification for the choice, except that there is a lot of studies being done where the land use is being identified, or land cover being identified to play important role. I mean, every hydrologic study portal is dealing with that.
Sure, but carbon from the atmosphere could be a scalar too.
Possibly. I don't know how can you do that on a regional basis or a local, but yes. These two are very location specific. They are at the kind of location, and they are making or kind of clarifying the difference between this spot and another spot. So that's what
And
was
you're
driving.
reducing this to a large scale, which is from the GCM. So then when you do the regression to the smaller field, how do you subgrid GCM field? Just regrid it with similar values across?
So I didn't catch the question.
Yeah, because when you develop a regression model,
Yeah.
you have a subgrid.
We,
You have a subgrid.
we did it for every pixel.
Yeah,
in
for every
space.
pixel, but then
Yeah.
your GCM grid is large scale,
Yes.
and then encompassing this
Yes.
subgrid scale. So and then your GCM field will be just
One
value
the
for
climate,
each- for each
the climate
grid,
variable will
and
be,
then you regrid it to say 1 kilometer, and then my GCM grid is 25 centimeter,
Sure.
25 degrees C, and this is 25 degrees
Yep.
C.
Yep.
My question is related to the physical scaling. So it seems that the uncover values information in the regression model that discrete number of values 4. Is that right?
sorry.
It means that the variable used in the regression model,
Yeah.
so is that the discrete number of the values 4?
Discrete number of
Value 4.
land use, yeah. We had actually, we used 14 land use categories, and each pixel is basically categorized. So very detailed analysis is being done on a pixel by pixel basis. So for each pixel, you will have that information in order to build that relationship, that regression relationship.
Yeah, but
with your
that is a code. It does not represent if it's green or brown.
No,
or
no, no,
something.
it's not the green or brown,
Yeah,
it's
so it's
actually
a
the
code.
type of land use.
Yeah, right.
So you have a percentage for every category. For this
Yeah.
percent, you have 10
Yes.
this one, 50
Yes.
this one.
Yeah.
Yeah, I'm just curious about why don't you use more physical property of the
Like
value?
NVDI or NVDI.
Possible.
Yeah,
This is the first time. This is the first time this has been actually.
Yes, NVDI, but then the problem would be the projections again.
So
with
things are-
NVDI and
You
NVDI.
need the future.
I mean that the physical property means that the more urban
Yeah,
heat
we-
capacity or roughness and for like
The point was that nobody was kind of thinking about combining it. So the first step and the first idea was, let's try to kind of combine them and see is this making any sense or contributing. And I am sure that there are different ways of kind of thinking how to expand. Yeah.
Steve,
I'll just quickly look at the GLM you compare. Did you use the same inputs then? You used
Yeah. Yes. For all the models we could release today. Yeah.
My question, I have one question. And my question is also related to the physical scaling.
Yeah.
I go back to the formula in physical scaling.
Yeah.
Physical scaling.
Sorry, wrong direction.
how to determine the f in the formula?
The function?
Function. What is, how to determine?
Time series.
Yeah, we utilize, yeah.
You're regressing.
Yes,
Regression.
the regression, and we use the bilinear, I have the information somewhere. I'll give you. Basically, these are the relationships that are developed, based on the. Yeah.
One question in addition to this. You define those f's independently upon each other or in multiple regression?
Multiple.
Multiple. What, why I ask so many predictors with multiple regression, certainly there might be a question on stability of this whole collinearity, etc., etc., etc.
We kind of we assess.
If you, I will
we
your
assess-
place, I would use an independent assessment for each.
There's a possibility to look into that. Yeah, I agree.
And,
It's
and one more question. You said that
Actually,
temperature is more sensitive to a selection of the model, which actually means to the first F1 and temperature large scale, yeah? While precipitation is more sensitive to
the
surface
physical-
properties.
physical
let us
properties,
say.
yeah.
Yeah,
Yeah.
no, physical properties, surface properties. To what degree it is different? Say for temperature, it means that the main is to have a good model. For precipitation might be to have simply a generator of white noise and surface, but correct surface properties.
Yeah. Okay, I'm not sure how to answer, I'm not sure how to answer the question. What we try to do is to kind of compare these different models, okay? And we did the comparison on the basis of the same, of the kind of same location and same input data and performance. So if they are fitting the white noise, they're all kind of fitting the white noise. I'm not completely sure, but I think we do have the particular mathematical representation that kind of tries to capture this idea, and all what we wanted is to see how they perform at the different locations from the point of view of contribution to the uncertainty, level of uncertainty. And we use the index, and I mean the traditional statistical tools to kind of do that.
So I have another question about this function of the precipitation. So I was wondering why land curve change have the impact on the change in the precipitation. So I totally agree with the temperature. The land curve change has an impact on the temperature, but I'm not sure the land curve change really affect the precipitation change.
It does. It does, because you have a number of processes that are affecting the precipitation, which are the consequence of the different land cover.
Did
you
you
have a
see-
grass compared to the forest and things
Sure.
like that.
But
For
that's
example,
depending on the
large-scale
time.
irrigation system can
It-
affect
I
the
think in
pharmacology, I mean local scale pharmacology.
Yeah, that's local scale.
We didn't look too much into agricultural literature, but we looked at, for example, in the urban areas, you have that kind of, the urban heat factor, which is basically the very, very clear indication that the local kind of conditions can affect that. Like if you get rid of all the greenery and everything else, and you create the urban environment, you have an impact on temperature and precipitation. I think it's probably through the combination of the processes that are involved there.
Is it possible to F is nonlinear? The F is nonlinear. In your studies, you assume to F is linear function.
Yeah,
But I think that
you can possibly expand into that. Yeah. We actually did provide some discussion on the different ways how that can be done.
Precipitation and temperature are kind of related too, right? So did you think about maybe combining those two into one, like a multivariate?
Not yet.
Not yet, yeah.
That's a possible way of thinking.
Yeah.
Yeah, could be one way of the. No, we didn't.
Yeah.
This is a very recent. What I am presenting is really
Mhm.
recent research, and results are, or the
Yeah.
publications are just coming. So we will continue. We will continue along two paths that we
Mhm.
want to finish this work. But if the people are interested, or new kind of researcher interested to continue that, I think that's one avenue to possibly think about.
Mhm.
Another thing probably that you could do is to compare the one that Alex
Alex can, yeah.
Alex